a angular part, let's call it the theta component, P theta, and a R component. So the momentum has two components, one along the angular direction and one along the R direction. What about P squared? P squared is the sum of the squares of both of them. So H is PR squared plus P theta squared over 2m. And that's it. But what about the angular momentum, the magnitude of the angular momentum? The magnitude of the angular momentum is P theta times R. Is that clear to you? That P theta times R is the angular momentum. R cross P. R cross P, the magnitude of it, is the magnitude of R times the magnitude of P theta. So, the magnitude of the angular momentum is equal to P theta times R, everybody, magnitude. Theta times R. Or another way to write it is that first of all, L squared is equal to P theta squared times R squared. Now let's write P theta squared is L squared over R squared. That was easy. And let's stick it into the Hamiltonian. PR squared plus P theta, oh, this is not, I'm sorry, you didn't correct me, plus V of R. Okay, PR squared, well that's just PR squared. H is PR squared over 2m. But what about P theta squared? P theta squared I think that's how I got invited. So, yeah, in this talk, I'd like to talk about our recent observation of D-wave nodes in the RPS spectrum of electron-doped strontium iridate. And so the D-wave nodes, upon heating, elongate to a Fermi arc of finite size length. This has nothing to do with Fermi arcs and wild semi-metal, but it looks very similar to cuprate behaviors. It's not working. So this, I think Inya did enough advertisement of my works. I don't have to. Okay, now it works. Okay, I don't have to tell this audience that combination of correlation and spin-orbit coupling gives rise to new exciting physics. Spin-orbit coupling alone has a profound effect at the level of single particle band structure, leading to a new quantum state of matter, a topological insulator. Now we want to add on top of this correlation effect by moving left in the periodic table to 4D and 5D transition metal oxide, in particular iridate. So there are predictions for correlated analogs of topological insulators, and we have seen some of the examples this morning. But even systems that are topologically trivial, systems can be interesting from the perspective of conventional correlated electron physics. So there are novel type of frontier magnetism of Kitai model, and then there's also a prediction for unconventional superconductivity. So magnetism in the presence of strong spin orbit coupling is interesting because depending on the bonding and lattice and bonding geometry, one can have very different kinds of magnetism, and one can realize exotic quantum magnets that go well beyond the conventional Heisenberg magnets. A prime example of that is the Kittai spin liquid, which requires a complete or near complete separation of Heisenberg interactions. And now there is a direct evidence from X-ray that the magnetism in honeycomb lattice iridate sodium to iridium-03, one of the candidate materials, the magnetism is indeed dominated by the so-called bond directional interactions that includes Kittai and other anisotropy terms. So it's exciting that one has a very different, radically different type of magnetism, but it is also interesting that one can realize a Heisenberg system as if there were no spin-orbit coupling in the system. So this leads to a new material candidate for high-TC superconductivity, and in fact there have been many discussions on possible superconductivity in strontium iridate. So the reason behind this is very simple, that strontium iridate, the low-energy effective physics is very similar to that of cuprate superconductors. So we don't understand what is the mechanism of high-TC superconductivity, but it is generally agreed that these are the essential ingredients of high-temperature superconductivity. So one needs a spin one-half moment on a quasi-two-dimensional square lattice, having strong antiferromagnetic Heisenberg coupling, and there shouldn't be any orbital degeneracy. So this may seem a rather simple recipe for high-temperature superconductivity, but in fact, cuprates are unique in realizing satisfying all these four conditions out of more than 300,000 inorganic compounds known to human beings. So until the discovery of strontium iridate, so this is the first non-cuprate material that satisfies all these four conditions. So it is isostructural to lanthanum cuprate, one of the high-TC parent insulators. And here, the orbital degeneracy is removed not by crystal field or Young-Color effect, but rather by spin or recoupling, which splits the 6-fold T2G levels into a quartet and a doublet, and the energy splitting is on the order of 0.6 electron volt. So with a nominal D5 low spin configuration, one hole occupies the so-called J equals 1/2, a manifold. So anytime you have a doublet, you can map it onto a pseudo-spin 1/2, pseudo-spin or isospin 1/2. But this J1/2 animal is an interesting object, having rather cubic shape, having almost equal mixture of